All right, gonna get started a couple minutes early today. I'm not feeling at my best, but we're gonna try to push through. Yesterday we were able to solve problem 12a of Advent of Code 2022, and today we will move on predictably to problem 12b. Let's just make sure that let's cargo test that. Okay, yeah, only problem 12b passes is failing. Sweet. So problem 12b. Day 12, he'll climb. Oh, this is problem 12a. Part 2. As you walk up the hill, you suspect that the elves will want to turn this into a hiking trail, naturally. The beginning isn't very scenic, though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked E, however the trail should still be direct, taking the fewest steps to reach its goal. So you'll need to find the shortest path from any square at elevation A to the square marked E. Consider the example. There are 6 choices. Here's one that's 29. Okay. So, the point of this one is now we have multiple choices of starting point, and we have to find the shortest path, or we have to find the one with the shortest path and get the number of steps. And so the naive way to do this is to just loop through all the A's and run our algorithm against each one. I imagine that the puzzle input has a lot of A's in it. Let's look, but I'm pretty sure. Yeah, I see a lot of A's. So that would be very slow, because that's just going to multiply the runtime, which is already like, I don't know, 10 seconds or something, by the number of A's, which we don't want to do. The alternative is to generalize Dijkstra's algorithm to construct a whole tree of shortest path. So if we start, yeah, okay. So the idea, I think, is going to be that we actually start at the ending point, and then we find the shortest path to every point on the grid. At least every point that every A. Actually, though, if we're using Dijkstra's algorithm, we don't need to go to every point, because the first one that we find that's A is guaranteed to be the shortest one. Oh, so this isn't bad at all, actually. This isn't bad at all. So let's write our test. So we will assert that solve problem 12b on get example input. Is that what it's called? Results in, what was it, 29? And obviously this will fail right now because there is no solve problem 12b. But the idea is going to be to start at the ending point and just run through Dijkstra's algorithm until we hit an A. Something at height 0. And so that's going to involve generalizing our get shortest path a little bit. It's also going to involve a new criterion, because we're going to start at E, which means that now our path can go down at most 1 and up any number. So get neighbors needs to be generalized. Get neighbors is what gives us a valid step. So if you remember from the first problem, you could go up at most 1 in altitude. Now we're going to be going backwards, so we can go down at most 1 in altitude. Let's just call this get inverse neighbors. It'll just be the same thing. In fact, I don't really know why I'm not just copying it. Except that we will check that it's greater than or equal to -1. And then our shortest path function so I think what we probably want to do is, instead of just having get shortest path, we'll want to have some kind of condition. So in here we're stopping. We have some sort of stop condition, right? So let's actually let's rename this get shortest path between, and then what we're going to do is have this just be self.get shortest path start, and then a function which says n equals end. And then this will be pub function get shortest path, take a self, take a start, and take an end condition, which will be a function of AU. What is this? What is node here? It's a function of vec2 to bool. And this returns an option vec2. And okay. And so now our end condition becomes end condition of node. Expected function pointer, you can't do it as a closure if they don't capture any variables. Yeah. Forget how I worked. I've run into this before. I forget how I worked around it. The idea is that this end condition is a closure, meaning it's a function that grabs variables from its environment, like end, which it's not allowed to do. For some reason. Closures can only be coerced. So this can this be an FN? Trait sized. So if I make this borrowed, but I can make it a reference to a function. I don't think this is going to work, though. This does work. Interesting. Okay. It's a reference to a function. Fascinating. Haven't really done that before. But hey, if it works, it works. Cool. And so now, and the other thing we want to be able to do is swap out the get neighbors function. And let's just have this be get shortest path use inverse neighbors bool, and so this will be use inverse neighbors, and this will be use inverse neighbors bool, and then we will match on this when we get our neighbors. So we need if use inverse neighbors, then self.get inverse neighbors node else. stuff. And so now, well, let's update the call sites. So these all need to have a false associated with them. And okay, same thing here. And what else? We'll need get inverse neighbors. Okay. And so now I think our problem, this one also needs this, amounts to get shortest path between. Use inverse neighbors will now be true. Grid.get ending point is where we'll start. And then rather than, and let's throw some parentheses in here, or indentation rather. And then rather than using shortest path between, we will do what? We'll just check for the elevation being A. So this will be I'm realizing grid.get n equals 0. Does this work? Am I allowed to pass a closure like this? I don't think I am. Get shortest path. That's the end condition, but it doesn't like it because I can't capture. Oh. This works. Wow. This is surprising. So basically I'm able to say is the node at 0. I'm able to capture the grid in the closure when I pass it in. This is very cool. This is very cool. Okay, and my code is compiling. Somewhat remarkably, perhaps. Let's see what happens. Home 12b fails. Problem 12a succeeds. And we get a number. Wow. So it got past the test just fine, and we get a number that's a little less. It's 512. Is that going to be it? That's it. Wow. Super cool. Super cool. Did not think that was going to be that easy at all. I think I've been missing out on the power of passing a reference to a closure. That's some pretty cool stuff. And we didn't even have to make our Dijkstra's algorithm more efficient, which I thought we might be needing to do, because I definitely didn't do the, like, I didn't use the proper data structures for it. Very cool. Very, very cool. Let's B passes. Let's just throw the answer in here. And we get to move on to problem 13. And it only took 20 minutes. Very cool. Definitely thinks for a bit, huh? Okay. Problem 13. Let's go. This is going to be the halfway point. Distress signal. Day 13. You climb the hill and again try to contact the elves. However, you instead receive a signal you weren't expecting. A distress signal. Your handheld device must still not be working properly. The package from the distress signal got decoded out of order. You'll need to reorder the list of received packets, your puzzle input, to decode the message. Your list contains pairs of packets. Pairs are separated by a blank line. You need to identify how many pairs of packets are in the right order, for example. Okay. Packet data consists of lists and integers. Each list starts with left bracket, ends with right square bracket. I should say square bracket because bracket means something different in British English. Left square bracket, right square bracket, and contains 0 or more comma-separated values, either integers or other lists. Okay, so it can be nested, and it can contain 0 elements. Each packet is always a list and appears on its own line. When comparing two values, the first value is called left and the second value is called right. Then, if both values are integers, the lower integer should come first. Okay. Got it. If they're the same integer, you continue. Okay. If both values are lists, then compare the first value of each list, then the second value, and so on. If the left list runs out of items first, the inputs are in the right order. Okay. If the right list runs out of items first, they're in the wrong order. If the lists are the same length and no comparison makes a decision, continue checking. Okay. If exactly one value is an integer, convert the integer to a list, which contains that integer as its only value. If exactly one oh, I see. If one side of the thing you're comparing are... Okay, got it. Okay, so the idea is basically, if you've got one number and you're trying to compare it to a list, you should be thinking of it as the list with that one number in it. Using these rules, you can determine which of the pairs in the example are in the right order. Okay. So 1, 1, 1, so the inputs are in the right order. Here we would go and compare these two. Those don't say anything. And this versus this, which is correct. Here we would say to left. Okay. Okay, I think this makes sense. What are the indices of the pairs that are already in the right order? And the first pair has index 1, the second pair has index 2, and so on. Oh, they're one indexed? Really? Okay. That's going to be easy to make a mistake. In the above example, the pairs in the right order are 1, 2, 4, and 6. The sum of these indices is 13. Okay. Cool. Let's do it. Let's get the puzzle input. And let's get rid of this. Let's get rid of this. Let's say assert equals. Get example inputs, solve problem 13a of example input should be 13. And we'll do function get example input. And the example input is this. Which is actually a little annoying. Let's actually not put it here. Let's put it in its own file. Input 13. And then this will be what? This will be example input, and we can use this, call it example input, and it will be example input 13. Ta-da. Hey, Dark Candy, please don't advertise in my chat. Okay. So that will set up the test. So how are we going to go about this? So this is going to be one of those things where the easy part is actually implementing it. The hard part is parsing it, which is slightly annoying. It shouldn't be too bad, though. I don't think we need to do like a prat parser or anything like that. So basically parsing it is going to be, we're going to want to do a recursive thing where we see a left bracket. Well, first of all, we're going to want to split it into pairs. Okay, that's easy. Second, if we see a left bracket, then we're going to enter into some function that can then recursively call more. Okay, I don't think parsing this is going to be too bad either. Now that I'm thinking about it, this problem in general doesn't seem very hard, compared to the last one especially. So what to do? Let's have a test that checks that we are parsing correctly. Parses correctly. And we will have what example input is. Let's just take this. So example input will say Let mute parser equals parser new. Do we want to use our... I don't even think we need to. I think it's just going to be a parser. Example input. In fact, do we even need a special parser? I don't think we do. I think we can just say let pairs, what are they, packet pairs, the packet from strings example input. We can assert that the length of the packet pairs is 8, I think it was. Yeah, it was 8. We can assert that packet pairs, let's see here, what's the simplest one? Packet pairs 5 is equal to going to be a little tree, right? So it's going to be like packet component, packet part, array or list, with nothing in it. And the other side is packet parts list with 3 in it. I'm just getting it from the example. Oh, does this need to be a packet part also? Yes, it does. And what's a nice, another nice one is 2. So we can do, which it's indexed as 2, so it's 1 in here, and then it's going to be a list of packet part list. Maybe I pop these out. And this will be a list of what? A list of 2 lists. Packet part list. This needs to be in a vac. There's a vac here, and then within it there's a list with just a 1, and the other one is 2, 3, 4, 5. just 2, 3, 4. Packet part N 2. Okay. Why did my... Should be fine. And then the other half is a list of... The first one is a list with one element in it, namely a 1, and the other side is n of 4. Okay. Alright, that should be a pretty good test of the parsing. And then we'll need to do the comparison, but the comparison is honestly, I think, pretty easy. So I think we just get to work on these. Parsing is going to be most everything. Okay, so let's derive not very much, debug and clone, I think, for now, and partial equals, and I guess equals, enum packet part can be a list of a vector of more packet parts, or it can be n of a u size. And okay, it's not offended by its recursive nature. And so let's impl packet part. And we want to get to pub function from strings. Strings will be a vec of string, and it will return a self. And here nope, that's not what it'll do. It will return a bunch of pairs, which is going to be self, and let's call this like parse packet pairs to be explicit. Can I parse packet pairs? And then this will be what? Here we're just gonna chunk everything up. So this will be, so actually our input parser can do chunks. Input is a vec of t, and it gives you a vector of vectors or a result. So let's actually input parser chunk strings 3. By the way, before I forget, let's fix the line endings here. And I guess at the end there's no line return, so maybe let's actually do strings dot into iter dot filter line l dot length is greater than 0. L dot chars stat length. Greater than 0. So then this will be let pairs be this, and then and we'll tell it that it's a vector. And then for each pair, we want to do something, namely pair 0, pair 1, so we're going to put it into a tuple, but we also want self from string. And we need to unwrap from chunk. Oh, I'm not quite doing this right. This needs to be out here. Yeah, so first we chunk, and then we map. Right, so we chunk into vectors. We chunk into vectors of size 2, and we need to unwrap that. Expect the input should be in pairs separated by white space. Okay. And at the end, we need to collect. And we can just return. And you know what? We actually don't need to. This should be a vec of pairs. That's a vec of strings. We map into pairs, and we call self.toString on it. Seems good. Why don't we want to map here? Vec string string. Fair point. Do there. Okay. And then we don't need to don't need to set that to any variable. Cool. So now we implement from string pubfunc from string s string self And here maybe we want to use our parser from the other problem, right? So parser, so we can just pass around a parser with this in it and do our parsing there. So let's do that. Let's say let parser equal parser new s. Let's import the parser. And now, and it should be mutable. And now we can say, so the parser just lets us pop things off that we need. It's really more of a lexer or a tokenizer. And we want to do a recursive thing where we say, let's just say self parse parser. And this will be function parse. It will take a parser and it will return a self. And so how will that go? It'll go parser dot, let's see here. Function get next token parser. And this will be a string in and of itself. And this will say match parser dot peak. If it is a left bracket, then we return. Maybe we should just tokenize it first. Because usually when you're parsing stuff like this, you first tokenize it into like an enum that corresponds to each thing that might show up. So like a left bracket, a right bracket, or a number. And I'm kind of skipping a step here the way that I'm thinking about it. Do I care? Yeah, I kind of care a little bit. Let's return a token here. And we'll say token left bracket. Token right bracket. If it's a comma, we do nothing. And if it's a number, it's a 0, a 1, 2, 3. There might be a nicer way to do this, but are these maybes? Yeah, these are options. thing, and otherwise we panic. Let's say unexpected character. Let's see. Okay, and let's say if parser dot length dot n remaining to parse equals 0, return none. We'll make this return an option. And that means that we can unwrap this. It will always return. And this ends up being the only tricky case then. So we'll let token be this, and we'll say return some token. And so in this case, we just want to consume until we hit either a comma or a let's say self parse number parser. This will parse number, parser. Let's always have it return, and let's say let s be parser dot consume until. Consume until a thing. I really thought consume until was a thing. Consume while. Sure. Is consume while a... It is a public function. Okay. I mean, it's easy enough to also have pub function consume until. I made self condition. It's just this. And it just returns what? It returns self.consume while not, or like C not condition C. Does this work? It won't let me capture it, right? This has the same problem as last time. Yeah, this has the same problem as last time. So let's actually update this to be a, what did we do? We made it a reference to a dyn function. And then these become references. Using our trick that we just learned. Nice. Looks like there's one more problematic one. Okay. Cool stuff. So now back in problem 13, we can consume until Um, C equals a comma, oops, or C equals a right bracket. Which should be the only possibilities. Or C is the end of the function. What happens if it's the end of the function? Consume while yeah, okay, it returns the whole thing. Great. So, and what's the issue here? Expected function pointer. Yep. Okay. So that will get us our whole number, and then we will s.parse what u32 should be fine. Can the numbers be negative? Put 13. They cannot. Okay, so u32 should be fine. Dot expect number should be parsable into u32, but was s. I think I have to wrap that. Close. That's close to what we want. Token n of this. All right, making some progress here. Let's have a new enum, and this one can have all the things. Enum token, and it'll be left bracket, right bracket, and n of u32. Okay, so we know how to parse the number. So we know how to get the next token. So now when we parse, we say what? So let's actually say, let's say self.tokenize. Tokenize. And this will just be while let some token be self get next token parser. Need to return as an empty vector, and push token, return token. Okay, return to return. Okay. Let tokens be this, and now now we want to say self from tokens. And let's call this tokenized number. And we can say function from tokens. Vec of token. Self. And here we want to be able, we actually want to be able to pop off the front of the list. So let's make this a queue. And we'll make this return a push back or push front? Push back. Yeah, that works. Because now we can say what? Match tokens dot pop front. If it's none, then we we can't return. What do we do if it's none? I think we don't want none to be an option. There should be at least one element in tokens. So it can be a left bracket, in which case from tokens. I think we need to kick back the remaining tokens also. So if it's a left bracket, which is actually the hard case, so maybe not the first case that we should do. Let's do an easier case first. Let's do token n. Then we just return self n and tokens. Here I said usize. Go to U32. Zero. So if it's a number, we just return. If it's a right bracket, then we return, then we panic, I think. Because if it's a left bracket, what we want to do is say while tokens get 0 is, no, it's not even that. Yeah, it is. While tokens get 0 is not equal to token right bracket. The bar checker is not gonna like what I'm doing here, but we'll sort it out. So here, let mute to return. Can be a new vector. And then we will say to return dot push self from tokens let right bracket be down here we say let right bracket be tokens dot pop front and in fact we can assert that right bracket is a sum token right bracket. Let's get rid of the underscores. And then return self list to return and tokens. If it's a right bracket, then we panic. Got a right bracket when parsing, which should never happen because of this case. And that's it, right? Those are the different types. And we should probably panic. Oh, well, yeah, we'll panic if it's empty. Okay. Let's return a reference. is. I am surprised that the bar checker is okay with me doing this. So we own tokens, we pop. It's mutable. So I'm pretty sure this has to be mute. We're popping there. Yeah, I feel like the bar checker doesn't like this, but it's just not getting to the error yet, but we'll solve that in a bit. Where let's see here. Packet pairs from strings. This should just be packet part. This should be parse packet pairs. This should be packet part n. Self list to return. Let's say let parsed new tokens be this, then we push parsed and tokens equals new tokens. Something like that. Still surprised the bar checker's not yelling. Self from string pair 0. Pair can't be moved. Get next token parser. Doesn't like me because I'm moving it in every iteration of the loop. This can be a reference. And this can be a reference. Mutable reference. Okay. Can't borrow, it is mutable. Alright. It compiles. I am surprised that this is okay. It isn't taking it by mutable ownership. And the match branches, and in each of the branches oh, it's copy. No, but it's a Yeah, I guess it's only borrowing one thing mutably at a time. Surprising, but perhaps true. Okay. Let's try running our tests. A couple of them should be in good shape. Okay, it's getting stuck in an infinite loop. Probably in here. Let's test. Let's try to test for tokenizing. Tokenizes correctly. Assert equal packet part tokenize parser new. So if we just have the number 1, then we expect to get a vector of token n1. But it didn't work. First number new. Consume until. Does it need to consume one more character? Yeah, it does. So this consume while plus self.consume n. And okay. So that's a simple case. Let's just do the same thing, but the number will be 190. We can stick a 0 in front of it, and it should still work. And that fails. I see. Tokenize number. Consume until. Actually, I don't think we want to do this. So we consume until it equals something, and that's consume while it doesn't equal it. And to do that, it consumes until that condition is true, which is to say that condition is false. But I want to return. This isn't going to fix the problem, but it's going to fix a different bug. Parser.consume 1. If parser.peakChar is a comma, then we want to consume 1 before we return. But okay, this is still not going to solve our bug. We can just look at the simple case. So consume until, consume while. So condition is some function pointer. Condition is the inverse of it being equal to one or the other of those things. To return is empty. Why? Because the condition was true on the first. Wait, isn't this already consume until? Consume white space. The condition is consume while it isn't white space. This is already consume until. This is just misnamed. It should be called consume until. And this does not need to be here. Okay, good. All right, what else? So it could be a list, in which case we want it to be token left bracket token 190 token right bracket. It can be a list with multiple elements. 1, 2, 3. Does it have spaces? It does not have spaces. In which case, this should have token n1, token n2, and token n3 in it. And here's where it runs forever. Alright. Let's take a look. We're not looping in here. Here's where we're looping. Get next token. Okay, so tokenized number is consuming, but otherwise it's not consuming, which we need it to do. Is there any reason not to just consume one here? Yes, there is. Okay, so we just parser.consume n of 1, and we'll say let left bracket be this, and same thing here. Let right bracket be parser.consume n1. Okay, and now we're getting proper failures, and our tokenizer passed. Very cool. Okay. So let's look at test parses correctly. In the wrong place. Okay. So what's going on here? Blah, blah, blah. Panicked at unexpected character, comma. That's logical enough. So when we tokenize a number, we need to make sure... Wait, this is during tokenizing. Oh, because you know what can happen? Is after a right bracket, there can be a comma. So we want to say if parser.peakChar is some comma, then let comma be parser.consume n1. Because at the end of an array, you can get a comma back. Nice, parser passes. Okay, I think that's the hardest part of the problem, because now we can parse our whole input, and so now we just need to be able to compare. And so let's set that up. Pub function. Just compare. Is ordered. Left, self, right, self. These can be borrowed, in fact. Returns a bool. And what to say here. So let's match left, right. So if they are both numbers, self n L and self n R, then oh, we have to continue though if it's not is ordered. L is less than R. We just return L is less than R, except that's not right, because L can be equal to R, in which case we need to keep doing the comparison. So, if L equals R, then okay, so let's say is ordered can be an option of a bool, and then we'll say return none. Otherwise, return L less than R. Sum L less than R. Yeah, we're not everything yet. Sure. Okay. And then if it's two arrays, well, if it's a number and a list, then we return is ordered of what? Of self list vec L R. I guess do we have to clone that? No, it's fine. And this should be a self n. What's wrong with this? Can't dereference. Yeah, I don't want to. I want to dereference this. And then this is expected reference found a list. Yeah, this should be a self list of this. Do I have to clone this? Can I just use right here? Nice. Okay. And same story if we're going the other way. Self list L, self n R is going to be self is ordered left, and at self list vec self n dereference R. And then the slightly more complicated case is self list L and self list R. And in this case, we go entry by entry. Is that right? I believe that's right. Yes, we go entry by entry. So we do let's see here. If we zip them, we get into problems. Left is smaller. L dot length, or left is at least as small. L dot length is less than or equal to R dot length. And then we do for ij in L dot iter dot zip R. Match self is ordered ij. If it's none, we do nothing. If it's some true, then we return true. If it's some anything, we return it. And then if we reach the end of the list, we say return left is at least as small. It needs to be return sum x. This needs to be return sum left is at least as small. Okay, I think this is right. And this just becomes what? Let pairs be packet parts, parse into packet pairs, input. Pairs dot into iter. We want to add up the indices. So we'll enumerate. We will map I comma packet. No, I comma pair. I comma left, right. And we'll say if packet part is ordered left, right, then I plus 1, else 0, and then we will sum it at the end. Tuple instead of individual arguments. Okay, if packet part is ordered left, right. And we expect this to always return, so we can unwrap here. If it gives us a none, it means it's ambiguous, I think, unless it means Otherwise, if the inputs are the same, if they're both, if the lists are the same length and no, then continue checking the next part of the input. Yeah, so it would be, ambiguous. Otherwise, okay. Cool. Let's try running this. So problem 13 fails with a real looking number. So it passed our main test, and we get a failure with 5609. Let's try it. 5609 is not right. Our answer is too high. Okay. What happened? What are the indices of the pairs that are already in the right order? The first pair has index 1, the second pair has index 2, and so on. In the examples above, they're 1, 2, 4, and 6. The sum of the indices is 13, and then we sum them up. And that already passed. 5609. That's what I just typed in, right? Yeah, 5609. And my answer is too high. But it's working on all of the is ordered. We add up the index. Alright. Let's read through this carefully. When comparing two values, the first value, if both values are integers, the lower one should come first. If the left is lower than the right, then they're in the right order. If the continue checking the next part of the input. Yeah. Okay. The left integer is higher than the right integer. They're not in the right order. Otherwise, we keep going. And we're always starting with a list. Both values are lists. Compare the first value of each list, then the second value, and so on. The left input runs out first. They're in the right order. This isn't right. I think it's left is smaller. And let's see. First off, I can do this down here and it doesn't hurt anything. So actually, I think what I want to do is say if L.length equals R.length, return none. And then otherwise we return some L.length is less than R.length. Okay, 5340 is a lower number. Boom. Okay. Just have to read the question right. Cool. Let's see. Let's read through the next one and see. I don't know if I can do it in 15 minutes. And like I mentioned, I'm not feeling great today, so I might stop early, but let's see. Part 2, and now you just need to put all of the packets in the right order. Disregard the blank lines in your list of received packets. The distress signal protocol also requires that you include 2 additional divider packets, 2 and 6. Using the same rules as before, organize all packets, the ones in your list of received packets, as well as the 2 divider packets, into the correct order. For the example above, the result of putting the packets in the correct order is that. Afterward, locate the divider packets. To find the decoder key, you need to determine the indices of the 2 divider packets and multiply them. That's indexed from 1. Okay. So we're doing some sort of sorting algorithm. We can do like swap sort, or what's the really famous one called? I can picture how the algorithm works. I can't think of the name though. Merge sort. So we already have a tree. So the point is going to be to parse them and sort them, and we can use quick sort. It's called quick sort. We can use quick sort. Which essentially works by swapping values around in a smart way. It's not even clear that we need to do it in that smart a way. How big is this? How big is this input? Yeah, it's like 500 long. Like, that doesn't need to be fast. Like, we can just get all the packets and swap them sequentially until they're in order. And it should work fine. Okay. I think I'm going to stop for today. This seems like a good time to stop. Let's actually go down here and put in the right value, 5340. And we'll push this. Whoops. And I will be back. Tomorrow is what? Tomorrow's Friday. I'm not sure if I'm gonna stream tomorrow. The next day is Christmas Eve, I'm definitely not going to stream on Christmas Eve. We'll see about probably not on Christmas either. So maybe I'll do tomorrow, maybe I won't. And either way, I'll be back on Monday, I would think, if not tomorrow. So hope everybody has a good one. Let's see if there's anyone to raid. Not really. All right, take it easy. Happy holidays, Merry Christmas if that's something you celebrate, and I'll see you soon. Take care.